So this mini lecture is concerned with the kinetic energy work theorem. And so from a very top level viewpoint, if positive work is done by the net force, the kinetic energy increases. If negative work is done by the net force, the kinetic energy decreases. That's essentially what this statement is. The work done by the net force is equal to the change in kinetic energy. So first of all, let me just give you a quick derivation. Let's say you had a mass m that was acted on by a force F, shown here in the x direction. And it had an initial velocity v0 pointing to the right, let's say. It underwent a displacement of delta x as shown here in the positive direction in this derivation example. And then it after undergoing this displacement while this force F is acting on it, it then has a velocity v1. So we'd like to use the kinematic equations to derive the kinetic energy work theorem. And so we know from the kinematic equations that v1 squared is equal to v0 squared plus 2 times the acceleration in the x direction times the displacement in the x direction. And if I take that whole equation and I multiply all the terms by 1/2 m, then I get 1/2 mv1 squared minus 1/2 mv0 squared. I've moved this term over to the other side here, is equal to m times a sub x times delta x. By Newton number 2, m times a sub x is F net. And so I can replace this with that. And F net times delta x is the work done by the net force. That's on the right side of the equal sign. On the left side of the equal sign, I have these two difference terms, but each one of these represents the kinetic energy. This the later potential energy, this the earlier potential energy, and the difference between those two is going to be the change in kinetic energy. So that's the kinetic energy work theorem. Let's look at two examples, and I've squeezed two examples in down here. First example, consider a 1 kilogram mass sitting on a surface with the mu sub k, a kinetic friction coefficient of 0.2. So let's assume that it's moving. And this 1 kilogram mass then has a push P applied to the right of 10 newtons and a backwards frictional force of S sub F. And it undergoes a displacement of 5 meters the whole time while it's displacing. This P and this S sub F is applied. And so let's say that initially its velocity was 2 meters per second going to the right. And finally, we'd like to know what the velocity is. Okay, so let's first of all calculate what F net is. F net is P minus F sub F. For bookkeeping purposes, we're assuming that the to the right direction is positive. And so that would be 10 newtons minus the frictional force is going to be the kinetic coefficient of friction times the normal force, but the normal force is just the weight in this case. So it's going to be 10 minus 0.2 times 1 times 10. In other words, 10 minus 2 newtons. The net force is 8 newtons to the right. And the work done by that force in a displacement of 5 meters to the right is simply going to be this 8 newtons times the 5 meter displacement. There's a 0-degree angle between those two, and so implicitly I'm putting that into the calculation here. The cosine of 0 is 1. So 40 joules of work are done by the net force. On the one hand. On the other hand, by the kinetic energy work theorem, that's equal to the difference in the kinetic energy. 1/2 mv1 squared minus 1/2 mv0 squared. And so you can see that if I know what m is and I know what v0 is, I can solve for v1. So what I proceed to do here is to put values in for everything I know. 1 kilogram for the mass here. I do not yet know what v1 is, or v1 squared. but I do know that V naught is 2 meters per second, and so that allows me, transposing this to the other side, to say that 1/2 times 1 kilogram times V1 squared is equal to 40 joules. That's the work done by the net force, plus 2 joules. That 2 joule term comes from here when it's put on the other side of the equation. 42 joules, and then V1 squared is equal to 2 times 42 divided by 1 kg. In other words, V1 is equal to the square root of 84. It's 9.2 meters per second. And so you can see that the object mass, this 1 kilogram mass, is speeding up as it goes to the right, and you know that from the kinematic equations and from Newton number 2, because clearly there's a net force going in this direction, this being bigger than that. Therefore, there's a net acceleration in the x direction, and therefore it will indeed speed up. Second example, let's consider a situation where we have a 1 kilogram mass, and let's say we have a net force, however it comes about, pointing to the left, and it's 1 Newton. And let's say that it starts with a 10 meter per second rightward velocity, and displaces 2 meters to the right, as shown by this red arrow, from here to here, and we'd like to know what the final velocity is. So the kinetic energy work theorem says that the difference in the kinetic energy, 1/2 mv1 squared minus 1/2 mv naught squared, is equal to the work done by the net force. But since the net force and the displacement are anti-parallel, the angle is 180, and therefore this is the negative of the magnitude of F net times delta x. It's negative. 1/2 mv1 squared is then 1/2 mv naught squared minus F net times delta x. And so V1 is equal to V naught squared, multiplying this through by 2 over m and taking the square root. V1 is equal to the square root of V naught squared minus 2 over m times F net times delta x. And V naught is 10 meters per second squared minus 2 divided by 1 kilogram times 1 Newton times 2 meters. And so this is 9.8 meters per second. It started with a rightward velocity of 10 meters per second. And after this happens, after it displaces delta x equals 2 meters to the right with a 1 Newton net force to the left, it slows to 9.8 meters per second.